Hi guys, today we're going to take a tour through simple number systems. Hopefully we'll be able to describe simple arithmetic operations and be able to answer some questions about how useful simpler number systems can be. So for example, let's just start off by talking about number systems. And by this I mean ways we can represent numbers. Usually we do this in our world with base 10. We represent things in decimals, and base 10, as we know, it has 10 digits ranging from 0 through 9, and we represent each number such that the place value to the left of each number is worth 10 times as much as the one before it. Another popular base system that you might know of is base 2. Now, this is the system that computers like to work with. It only has 2 digits, 0 and 1. Instead of changing the value of each place value by 10, it changes by 2. So if you wanted to write 10 from base 10 in base 2, you would need 4 digits instead of 2. Partially because base 2 is a simpler number system. You need more digits to express the same number. And so the question is, can we go simpler than this? How about base 1? No one really talks about this because base 1 by itself is not that useful, but it does give us some great ideas. So first things first, base 1, we extend it, it only has 1 digit. Just so we don't use 0, let's use 1 in that place. And instead of changing the place value by times 2, as in base 2, we change it by times 1. So every single place value has exactly the same value. So we're only going to be dealing with natural numbers for now, but you could see a slight problem. For example, if you had 11 in base 1, that would have a value of 2. But that would also be the same as 1.1 because the 0.1 in the decimal place has the same value. But let's not worry about the decimal place at all. Okay. So in this base 1 system, this base 1 system is even more simpler than the previous two systems. If you want to express 10, you need 10 whole digits. So you might wonder, how is this even useful to us? Because we do everything in base 10. Not to worry, we're going to get to that eventually. However, base 1 is close to a mathematical formulation of the natural numbers, where we start by defining 0. And we define a successor function that takes a natural number and returns the natural number that is 1 higher than it. It returns the successor of the natural number. So if we started at 0, we would say 0 is the same as 0. 1 would be the successor of 0. 2 would be the successor of 1, which we know is the successor of 0. So we would need 2 applications of the successor to 0, and so on. So we would just say, in this case, that n, for any natural number, it's just applying the successor function n times to 0. And this is basically the same idea as base 1. In base 1, we'll need n ones to represent the number n. And the same thing in this successor version, we'll need n applications of the successor function. Now, this seems very inefficient, but stick with me for just 1 second because we're going to abstract. So the idea is we're going to abstract away the 0 and the s, and we're going to turn each natural number into a function that takes in 2 arguments. One represents a successor function of sorts, and the other represents the 0. So for example, in this case, 0 would be the same thing as saying it's a function which takes in some function f and x and just returns x by itself. For 1, we'll say that it is also a function that takes in 2 arguments, but this time it applies f to x. Similarly for 2, we'll say that it's a function that takes in 2 variables and returns f applied to x twice, and so on. So in fact, we'll define n as a function that takes in 2 arguments and applies the first one, which should be a function, n times 2x. Clearly, this is very similar to our successor definition of the natural numbers. although it's not the same thing because we have completely abstracted away the 0 and the s, which will be very important. Okay, so I finally brought you down to the simplest, possibly one of the simplest number systems I know of. How could we possibly use this? If we do want to use it, we have to be able to do basic arithmetic operations on it. So that's exactly what we're going to do. We need to define basic arithmetic operations. So let's try operations. So the first operation we need to do is actually simpler than addition. It's going to be the increment function. It's essentially the successor function. We need to turn for every for an input of n, we need to change this f to the n to f to the n plus 1. So essentially it acts as a successor function. Okay, so the first instinct we might have to make this increment function is to take an argument n and simply return f of n. However, n is also a function that needs to take in the same f. We need to make sure that f on the outside is the same as the f inside the n. So we need to make sure n takes f as well as x, as it's defined here. And remember that this increment function is returning a natural number. Our natural numbers are functions that take in 2 parameters, so we need to make sure we have 2 extra parameters in addition to n. So now when we apply increment to n, okay, we should probably try some examples. So what happens when we try to increment 0? So if we try to increment 0, we'll get f of 0 and taking in parameters f of x. We remember that 0 simply just returns x by itself. So this is f of x, which we know is defined to be 1. So we see that if we increment 0, we get 1 after it. Okay, brilliant. Similarly, if we take any number n with parameters f and x, we'll be able to apply an additional f on top of the n, and therefore transform this into f to the n plus 1 applied to x, which is simply just n plus 1 applied to f of x. So indeed, we have created an increment function. I'm also going to define an additional function called inc prime. And the reason I'm doing this is so that is because sometimes we want to rearrange the order of the arguments for our functions. In this case, I'll stick the f of x first, and then the number n which we want to increment. Okay, and we'll simply define it as the increment function applied to n and then f of x. Okay, so now we have an increment function. Let's try adding. So if you think about adding, all adding is its repeated incrementation. So if you wanted to add, for example, f of x to f of x, we'd simply need to have 3 f's in a row. Another way to view this is to say, hey, why don't we just substitute this f of x in for this x in the first place? And when we substitute it in, we'll in fact get f of f of x. And yet another way of thinking about that is if we substitute f of x in there and then increment it 2 times. And we can do precisely that. So for this add function, we'll need to take in our 2 arguments, 2 integers m and n, and we'll need to feed in f and x as well, once again, because we're returning this sum as an integer, which takes in f and x as arguments. Okay, and now that we have that, here's how we're going to define add. We're going to take n, and instead of f, we're going to use the increment function. We're going to feed in f and x to inc prime, which can take in the integer as a next argument and increment it. Now, instead of x down here, we're going to write the other integer, m, and we're going to feed in f of x here. Okay, so what we've done is exactly what we called for. Instead of x, we substituted in the number m. Instead of this regular FFF business, we decided to repetitively increment our m n times. And so let's give an example of what this looks like. We're going to add 2 and 2 together, and we're going to feed in f of x. So in this case, we have 2 increment f of x and 2f x. Okay, so now substituting in the definition of 2 down here, we have 2 of increment fx, and then f of x. So now we have to apply the increment function twice. So increment of fx applied to increment of fx applied to f of x. Now we simplify. So simply just and now we have 3x. And again, we'll have 4x. 1, 2, 3, and 4. Which, of course, we know is 4. And 2 plus 2 is 4. So bingo, we've got it. We've got addition through a repeated incrementation. Let's try to go one step higher. We're going to define multiplication and subsequently exponentiation quite in the same way. It's not going to be that hard once we've gotten this far. So the first step is actually to rewrite the add function once more. We're going to define add prime by rearranging the arguments. So we take fx and the first number m first, and then we're going to take n. And so this will simply be equivalent to just adding m and n together. Now to define multiplication, if you think about multiplication, it's just repeated addition. So we'll take in our two integers, m and n, as well as our function f and variable x. And we'll just rinse and repeat. So we'll start with n. And what are we doing n times? We're going to add m n times. Okay, so the function we're going to use is add. And so we're going to make sure we feed in f and x first. And we'll feed in m. So now this add prime function is primed to add m to its next argument. And so whatever its next argument is going to be, that's what we're going to add to. So if we think about it, what are we adding m n times to? We're going to add it to 0 n times. So simply, instead of writing x inside of the arguments for n, we're going to write 0. And we're going to make sure we feed in f and x. All right, so here we have it. We're going to add m n times to 0. Okay. And as a quick example, we can multiply. I'm going to abbreviate a little bit here, but we can multiply 3 and 2 together. So we multiply 3 together, you get 2, and then you have to add 3 to 0. So this is simply something like this: simply add 3 to add 3 to 0. Of course, just add 3 to 3, which is just 6. And clearly, our multiplication has worked out. One more step. And once again, we're going to define a prime function by just rearranging the variables. So now for exponentiation. So exponentiation is simply repeated multiplication. Yeah, so we'll take in our two arguments, m and n. What's different about this one is that exponentiation is not, you can't switch around m and n all the time. So we're going to interpret this as m to the nth power. And we'll define it pretty much exactly the same way we've done everything else. We'll start with n, like that. And so what are we doing n times? We're going to multiply m n times. That's what exponentiation is about, repeated multiplication. So the function we should put inside of here is multiplication, feeding in f and x, as well as m. And what are we multiplying by? What's going to be our x? If we put in a 0, 0 times anything is 0. That's not going to do work for us. What we need is 1. We're going to need 1 in here. Okay, we're going to have 1, and we're going to feed in f of x as well. So for example, if we wanted to calculate 2 to the third, this would just be the exponentiation of 2 and 3. I'm going to abbreviate the f and x out of here for simplicity. This is simply just 3 multiplied by 2 and 1. Now we're multiplying 2 by 2 3 times. So we have multi, and 1. And now we can start multiplying. And you'll see this eventually will just simplify all the way to 8, which is exactly our expected result. And we can keep going with this. We can generalize this repeated operation. It's known as hyperoperation. The next step after exponentiation would be tetration, and after that pentation, and so on and so forth. And all the ones after exponentiation, they all use 1 as the base of the repeated operation. Okay, so what have we actually done here? We've defined a system for the natural numbers that are known by the Church numerals. They're named after their inventor or discoverer, Church, from like early 1900s, and he did a lot of cool computer science work. And we defined numbers as functions, right? We define natural numbers as functions that take in a function f and some x. And we were able to define all the regular arithmetic operations, like successors. We were able to define addition, multiplication, exponentiation, and so on. And the cool thing about this is that this is a really simple system. Why is it super simple? It's because we didn't actually have to define anything. All we needed to assume is that functions exist. We don't need to know what 0 is. We don't need to know what successors are. All we assumed was that we can have functions and we can apply functions, and we can have multiple arguments for functions. That's all we had. We didn't need any digits or anything. A super simple system. And through this super simple system, we were able to rigorously define arithmetic operations. And the thing about this rigorous definition is it's useful for in some programming languages, especially functional languages. Their programming language is actually built on this sort of mathematical structure where we only use functions, known as lambda calculus. In those kind of programs, they can generalize the natural numbers as we've done here, and they can use it to do things like proofs about the natural numbers. Another cool thing about this simple system is that it always works. As in, if we can input anything we want into these add and successor functions and multiply, we can put in whatever numbers we want, and they will always work. And one of my favorite things to do with this is to answer this question. What is 0 to the 0th power? Everyone knows it's undefined, but I just told you that all the operations are defined in these church numerals. So we should be able to get an answer. Now, if we take the exponential of 0 and 0, and I'll include the f and x this time, we'll be able to say, by definition, this is 0 by 2, multiplication by 0, multiplication by fx0, 2, 1, fx. Okay, now here's the thing. We could evaluate this function here, but if you notice this 0 on the outside, remember this 0 only returns the x argument. Okay, so this would only return 1 f of x, which is just defined as 1. So the answer to the age-old question, 0 to the 0th, is 1. Of course, the catch here is that everything we've done here is just pure formalism. It's just definitions. However, the definitions feel very natural. And I hope this was a cool exploration into number systems that are even simpler than binary. Even simpler than using digits, we've used functions here. So have a good one.